Good morning, everyone. Yesterday, we talked about the current and what is the current, the model of current, and how current came out, and the batteries and EMF. What is EMF? It is the maximum voltage, electric potential difference. Yeah, if you review the battery in supermarket and you find there will be the AMF like in the package like 1.5 volt. Yeah, and like that. And we also talk about the uh, uh, the uh, relationship, how to calculate the current, how to define the current, describe the current. Yeah, this is what we talk about last class. Yeah, and this class we will continue to talk about the current. And we will talk about how potential and the current connecting. We know potential differences, voltage. Yeah, we usually talk about the voltage, but it is just like the electric potential difference. And how potential and current connecting, we will talk about in this class. And then we will talk about Ohm's law. Actually, it's a very famous law for the circuit. It just talk about the relationship between the current, voltage, and resistor. Resistor. Yeah. Oh, yeah. We also talk about the resistor. What is resistor, and how to define it. And finally, we will talk about the energy and the power. Yeah. This is what we talk about today's class. Okay. Let's begin today's class. First, let me share my screen. Okay, yeah. For today's class, we will continue to focus on current and resistance. And yeah, the we know the goal for the chapter 22 is learn how and why charge moves through a conductor as a current. Yeah, we have already learned what is a current, the model of a current. Yeah, we will continue to learn more information about current. Okay, yeah, this is today's class goal. And firstly, we will review current and batteries. Yeah, we talk about it in last class. And then we will talk about how to we will try to understand how potential and current connecting. And next, we will learn Ohm's law and resistor circuits. And finally, we will study energy and power. Yeah. Okay. Firstly, let's review the current and batteries we learned in last class. Yeah, we know the current is defined to the motion of positive charges. Actually, we talk about this in last class. Actually, the current is the motion of charges. Usually, the charge is the negative charge, like electron. Yeah, because like atom is just a fixed, and the electrons can be can is easy, is free to move. But you can see the electron moves for example towards to this direction, which is the same thing, is same thing like the positive charges move to this direction. Yeah, it actually it's the same thing. So we just define the current is the motion of the positive charges. Yeah, yeah, because like in a neutral atom, the positive charge and the negative charge is the same thing. So this is we just define it. So using this equation, yeah, you can see this is like a capacitor, like a parallel plate capacitor, and this is a positive like a plate and this is negative. Actually, it is like the plate discharges as negative charge enters into this yeah this plate discharge as negative charge leaves it, and then uh like the negative charge enters into this positive plate and cancel its positive charge. This is a real situation for the parallel plate capacitor. But we also can consider this motion as like this plate discharge as positive charge leaves it and go to this one, and this plate discharge as positive charge enters it and cancel its negative charge. Actually, it's we can consider this process as this process. It's the similar thing, yeah. And for the battery, yeah, we know like for the battery is different with the capacitor because there is no plate here. So like for the battery and the charge isolated as as escalator, yeah, the charge escalator lifts charges from the negative terminal to the positive terminal. Yeah, and the charge Q can gain energy. This one, yeah, we talk about this in last class. And once the charge reaches the positive terminal, they fall downhill through the well back to the negative terminal, and form the circuit, and then the current can go through the wire. Yeah, this is how the battery work. Yeah, and we also talk about EMF. Actually, this is the maximum like potential difference for the battery. Yeah, and yeah, this is what we talk about in last class. Yeah, this is the main thing, main content for the last class. Yeah, today we will firstly we will talk about connecting potential and current. Yeah, you can also see some videos for the current and resistance, like and I will now play this video here. Okay, yeah, a battery is a source of potential difference. Yeah, we talk about that. Yeah, the current that flows through the a wire connecting the battery terminals is a consequence of the potential difference. Yeah, we just we know like the current is a source of potential difference, and the current that flows through a wire connecting the battery terminal is a consequence of the potential difference. Yeah. And because the ends of the wire are connected to the terminals of the battery, the potential difference between the two ends is equal to the potential difference between the battery terminals. Yeah, for example, here is a battery, this is the positive, this is the negative, and then you use a wire connect to it. And actually the the difference like between the two ends of the battery. This is the difference battery potential difference for the battery, and this is for the wire. Yeah, like actually it is equal like the wire. Yeah, the wire is one connect to the positive and the other connect to the negative. So which means those two are equal. The potential difference causes a current in the direction of the decreasing potential. Yeah, which means the potential difference causes a current. Yeah, the decrease potential here is negative. Here is positive. Here is negative. So this here has a higher potential. Here it has a lower potential, which means the current direction is just from positive to negative. Yeah, that makes sense to you. Okay, let's talk about this one. What factors affect current's magnitude? Yeah, like two factors determine the current. Yeah, there are two factors determine. Yeah, maybe someone will be confused. Like we talk about the I equal what delta Q delta t, am I right? Yeah, divide delta t like the in a unit time, how much charge goes through. Yeah, we define the and the current is equal this like in last class, but you can see the charges and the time is like will be changed. So yes, actually there are some like fixed thing. Yeah, for this for battery. Yeah, what is factor affect the current's magnitude? Actually, there are two factors. Yeah, those two factors actually is fixed if the battery is fixed. Yeah, one is the potential difference, and the other is the properties of the wire. You can see if the battery is fixed, the potential difference is fixed. For example, you buy a battery in supermarket and the EMF is 6 volt, which means the potential difference is 6 volt. It will not be changed. Yeah, and the properties of the wire. Yeah, you can see if the wire is fixed, like if you just grab a wire from a lab, which means the property of this wire is fixed. Yeah, those fixed thing can determine the current for this situation. Yeah, the current is proportional the potential like a difference. Yeah, which means if the potential difference is bigger, which means the current is bigger. If the potential difference is smaller, and the current will be smaller. Yeah, adding a second battery increases the potential difference. Actually, we talk about this in last class. If two batteries connect like in series, and then the potential difference is two potential difference plus together. Yeah, which increases the electric field and therefore the current. Yeah, because yeah, the current is a proportion the potential difference. Yeah, that makes sense to you? Okay, let's continue. Yeah, let's talk about continue to talk about the resistance. Yeah, increasing the length of the wire connecting a battery decreases the current, which which increases the thickness of the wire, increases the current. Yeah, like well, sorry, like if you increase the length of the wire, yeah, and which means this wire like become, if it become longer and thin, which means the current will be small. If this wire is short and thick, and this means the current will be large. And yeah, think about that. When you like observe some like electric things in the real world, if the cable, if the wire, if the cable connect to the two different equipments, and if the cable is very is thick and short, which means it can go through the large like current. If it is very thin and long, it will mean it can go through the small current. You can see usually in our lab, yeah, we use the wire and they are very thin. Yeah, but in the real world, you if you observe it and the like the wire and the cable is like usually it is thick. Yeah, because in the real world the current usually is bigger than in the lab. That makes sense to you? Okay, we will talk about why it's like why it is just like this. Yeah, it's related to the resistance. Okay, wires of different material will carry different currents. Some materials are better conductors than others. Yeah, this is a yeah. For example, a copper wire carries a large current than an iron wire of the same dimensions. If you are familiar with like electric things, you will know like in our house like usually the wire is copper wire. Yeah, not the other like iron wire. Yeah, because the copper wire can like carry a larger like a current. Okay, yeah, and we will talk about why this situation happens. Why like the long thin wire like only can carry small current, and the short thick wire can carry large, and also different material like are better than others. Yeah, actually it's related to resistance. Yeah. Yeah, the resistance we use R to represent it is a measure of how hard it is to push charges through a wire. A large resistance implies that it is hard to move charges through the wire. Yeah, the current depends on the resistance of the wire and the potential difference between the ends of the wire. Yeah, this is I equal like the potential difference and the resistance. Yeah, actually, why is just like this? Because some material Yeah, the copper, for example, actually the copper has smaller resistance. Yeah, which means it is smaller, the current will be large. And also like the thick and shorter wear, which means the small like resistant, and this long thin wear, which means the like big resistance. Yeah, that's the reason why this situation happened. Okay, yeah, the where's the resistance? Yeah, because we know the current equal what? Equal the potential difference divide resistance. Then from this equation we can get this equation. Yeah, the resistance is equal like the potential difference divided current. Yeah, the S unit of the resistance is the ohm. Defined. Yeah, we use this symbol to represent it. 1 ohm. This is a short for this one, and equal 1 volt divided A. Yeah, because you can see here. Yeah, and this is Ohm's law. Yeah, we will talk about later. Yeah, and let's check some quick check questions. Yeah, the current through a wire is measured as the potential difference. Delta V is varied. What's the wire's resistance? You can see here. This is delta V. This is I, which R equal what? Equal delta V divided I am, right? Yeah, just we talk about that. And you can see here, yeah, you can just get one value. Yeah, from here, if the voltage is 1 and the current it is around like 15, I'm right? So which means the resistance is 1/15. What's the value? It is this one, I'm right? Actually, you also can use this one, a 20.0, which means 100 divided 25. Yeah, it is also this value. So which means the resistor is 0.02 ohm. Yeah, yeah. Actually, yeah. This one is inverse of the loop. Yeah. Okay. If the is a inverse of a slope, do you know why? Yeah, because you can see here. This is this one. So the delta V equal what? I R I am right, and which means I should be the x value and V should be the y value. But here is the opposite, so that's the reason why it is the inverse of the slope. Yeah, that makes sense to you. Okay, let's continue to talk about one example, like a resistance of a light bulb. The glowing element in an incandescent light bulb is a filament. Yeah, and a long thin piece of tungsten wire that is heated by the electric current through it. When connected to the 120 volt of an electric outlet, a 16-volt bulb carries a current of 0.5 like ampere. What is the resistance of the filament in the lab? Yeah, we can use the equation 22.6 like R equal delta V divided I, am right? Yeah, just this equation. And we know the like a potential difference 120 volt, and we know the current, and then we can calculate the resistance. Yeah, it is 240 ohm. Okay, yeah, as we see, yeah, the resistance of the filament varies with temperature. This value holds for the light bulb only when the bulb is glowing and the filament is hot. Yeah, okay. Yeah, let's talk about the other term called resistivity. Yeah, resistivity, we use this symbol to represent it. Characterizes the electrical properties of materials. Yeah, materials that are good conductors have low resistivity, such as copper. Yeah, we talk about like the copper had like a we talk about copper like where later. Yeah, and the materials that are poor conductors and thus good insulator has high resistivity, such as paper and some like wood. Yeah, it has very high like resistivity. And actually the resistivity of a metal increases with increasing temperature. If the temperature like increasing, yeah, and the resistivity of a metal will increase at the same time. Yeah. Okay. Like let's aware made of a material of resistivity, this one, and with length, this one, and the cross section area has resistance. Yeah, this is the definition for the resistance. Like actually the resistance of for a material, it is fixed. Yeah, it depends on the resistivity. Yeah, and the different material has different resistivity, and the length and the area. Yeah, which means the longer material, which means the resistor will be bigger, and the area, which means if it is thick, which means this will be bigger, and the resistance will be decrease. Yeah, we just talk about it. Yeah, that's the reason why. Yeah, because the resistance is can be defined as this equation. Yeah, resistance is a property of a specific wire, since it depends on the conductor's length, diameter, and the material. Yeah, and yeah, this is some resistivities of material. Yeah, common materials. The copper. Yeah, you can see. Yeah, the resistivity is small, and aluminum, and yeah, this one, and other things, other like common things we usually meet. And when you calculate, when you like resolve some problems, you may need these resistivity materials. Yeah, you can check this box. Okay, let's talk about one some example problem. Okay. Yeah, the filament of a 100-volt bolt carries a current of 0.83 A at the normal operating voltage of 120 volt. What is the resistance of the filament? And if the filament is made of tungsten, where of diameter this one, how long is the filament? Yeah, actually we can use the equation like here the resistance equal what? Equal V divided I, I'm right, and V is what? 100, and I equal this one, and then you can calculate the resistance. And for the for this question B, and we know like uh, the tungsten, for the tungsten, like resistivity is this one, because it's in the normal temperature. And then we use this equation R R equal L divided A. And then here we know the resistance. Yeah, we have already calculated, and we know this one here from this box, this one, and then we know the area, because we know the diameter like this, and then we can calculate the length. That makes sense to you? Okay, I will leave this quite a problem to you, and let's review the other quick check question. Yeah, wire 2 is twice the length and twice the diameter of wire 1. What is the ratio of R2 divided R1 of their resistances? Yeah, let's write down the resistance like here. A, I'm right. And here there is 2, and those two like has the same material, so this one is the same thing. Yeah, R2 equal, this is the same, and L for the R2, which means the length is two twice this one, and the diameter is also the twice, so which means this one should be 4A, because it equal like 2R square, am I right? So which means it is 4A. This is the R2, and this is R1 equal LA, and this is 2. And when you like divide those two, which means it is 1 divided 2, it is half. So the answer should be B. That makes sense to you. Yeah, you just use these equations and to calculate to it. Yeah. Okay. Let's talk about this example. The length of a light bulb filament. Okay. Okay, let's talk about this example. Yeah, the length of a light bulb filament. Yeah, we calculated in example 20.2 that this one. Yeah, sorry, not this one. Yeah, this one. Yeah, and yeah, and that 16-watt light bulb has a resistance of 250 and 40 ohm. As the operating temperature of the tungsten filament, the resistivity is approximately this one. Yeah, actually we can search this in this table here. Yeah. Uh, yeah. Because it is in a operating temperature, it's like a high. Yeah. If the wire used to make the filament is this 0.040 millimeter in diameter. Yeah. How long must the filament be? Yeah, actually we can use the equation. We talk about that. The resistance of a wire depends on its length, its cross-section area, and the material of which it is made. So we can use this equation. So you should firstly let's calculate the area, the cross-section area of the wire. Yeah, it is pi r square. Yeah, this is area, and we know the pi, we know the r. Yeah, this is what we know. Yeah, here. Yeah, the diameter is a 0.04. Which means the R equal half that is equal 0.02. Yeah, that makes sense to you. Yeah, and then it equal the final result for the area is equal this one. And then we use the equation like R equal L divided A. Yeah, which means the L equal what? RA divided the resistivity. Yeah, we know the A, yeah, because we calculated it, and we know the R, yeah, we have calculated before. And then we know this one, and then we can calculate the length. This is 0.6 meter. Yeah, this is quite long, nearly like 2 feet. This result may seem surprising, but some reflection shows that it makes sense. The resistivity of tungsten is low, so the filament must be quite thin and long. Yeah, you can see like in the bulb. Yeah, the yeah, the tungsten is it is like a circle, like a if you like extend it and measure it, yeah, it nearly 2 feet. Yeah, maybe you can measure it like 1 day. Yeah. Okay, let's continue. Yeah, let's talk about the electrical measurements of physical properties. Yeah, different tissues in the body have different resistivities. Yeah, like we can find it in this. Yeah, you can see the fat, the blood have 1.6 like me like this is the muscle, this is the fat, this yeah, this is cell membrane. Yeah, which means yeah, different tissues in the body have different resistivities. Fat has higher resistivity than muscle, and so a higher resistance in the body indicates a higher like a proportion of fat. Yeah, that makes sense to you. Electrical impedance tomography passes a small like current through a patient's torso to measure the resistance of in intervening tissue. Yeah, you can see we can use like the electrical impedance tomography. Yeah, to pass a small current through a patient's torso to measure the resistance of interval tissue. Yeah, we can. Yeah, this is an image of a patient's tussle generated from the resistance between many pairs of electrodes. Yeah, we like talk about in last class. Yeah, like in chapter 22. Yeah, you can use the electrodes to like measure the patients like current and resistance like that. Yeah, yeah, showing decreasing resistance in red, which means here. Yeah, which means here it's the decreasing resistance, which means the resistor here is smaller, and an increasing resistance in blue, which means this here the resistance. Here the resistance is bigger. Yeah, which means like the lungs contain more like fat, because fat has a higher like a resistance. Yeah, you can see here the fat has a higher resistivity, yeah, than muscle. Yeah, and then the heart, because it has a smaller resistance, so which means that like the heart maybe has contains more like muscle like that. Yeah, blood is a better conductor than tissues of the heart and lungs. So the motion of blood decreased the patient's resistance of the heart and increased that of the lungs. Yeah. Okay, yeah. In a patient with circulatory problems, any deviation from normal blood flow would lead to abnormal patterns of resistance in this image. Yeah, actually, yeah, this image is a like a normal one. But if one patient has a circulatory problem, then this image will become like a abnormal. For example, here maybe it has the higher resistance, and here it has a lower resistance. Yeah, that makes sense to you. Okay. Okay, this is an application like for resistance in our human body. Let's continue to talk about Ohm's law and resistor circuits. Okay, yeah, Ohm's law. Actually, we just talk about the Ohm's law. Like Ohm's law describes the relationship between the potential difference across a conductor and the current passing through it. Yeah, this is what the Ohm's law. Yeah, the current like depends. Yeah, the current depends on the potential like electric potential differences and the resistor. Yeah, we talk about it like just now. Yeah, the Ohm's law is not a law of nature. It is limited to those materials whose resistance R remains constant during use. Yeah, yeah. If the consistency change like during use, and you cannot use the Ohm's law for that. Yeah, materials to which Ohm's law applies are called ohmic. Yeah, if we can call these materials ohmic. Yeah, and you also can view this class video for basic circuits. Yeah, I will not play this video here. Okay, let's continue to talk about Ohm's law. Yeah, the current through an ohmic material is directly proportional to the potential difference. Yeah, we know the I, yeah, equal like a delta V divided R. Yeah, so which means the current through ohmic material is directly proportional to the potential difference. Other material and devices are non-ohmic, meaning the current through the device is not directly proportional to the potential difference. Non-ohmic devices include batteries and capacitors. Yeah. So which means for the batteries and capacitors, we can now use this equation. Yeah, this equation is just for the ohmic material. This is the current is directly proportional to the potential difference, and the resistor is the 1 over slope. We talk about y. Yeah, because you can see the delta v equal Ri, right? Which means if it is slope and the axis value should be I, and the y should be delta v. So, but here it is opposite, which means like I equal R delta v. Am I right? So this is just the 1 over slope. That makes sense to you? Okay. Let's continue to talk about resistors. Yeah, the resistors are circuit elements that are designed to have certain resistance for practical reasons. Yeah, there are a few basic types that will be very important as we start to look at electric circuits in detail. Yeah, let's review that. Yeah, you can see. Actually, for the resistors, we can talk about the heating elements. As charges move through a resistive wire, their electrical energy is transformed into thermal energy, heating the wire. Whereas in a toaster, you can see there is an example. Whereas in a toaster, a stove burner, or the rear window defroster of a car are practical examples of this electric heating. Yeah, like if charges move through this wire, this resistive wire, and their electric energy is transformed into the thermal energy. Then it heating the wire. Yeah, so it will generate the heating. Yeah, it will have the thermal energy. Yeah, this is the conversation of conservation of the energy. We will talk about later. Yeah. Okay. And for the resistor, we also can use it for the circuit elements. Inside many electronic devices is a circuit board with many small cylinders. These cylinders are resistors. Yeah, you can see here. Yeah, that help control currents and voltages in the circuit. And because you can see here the I equal delta V R. Yeah, if you want if it's a voltage difference, if the potential difference is fixed, yeah, and you want the smaller current, which means you just make the resistor bigger. And if you want the current bigger, and you just make the resistor smaller, yeah. It's the same thing for the potential difference, like the voltages. Yeah, the colored bands on the resistors indicate their resistance values. Yeah, the different colors represent different value. Okay, yeah, you will know that if you do the lab. Yeah, a resistor whose a resistor also can be used as a sensor element. Yeah, a resistor whose resistance changes in response to changing circumstances can be used as a sensor. Yeah, you can see here there is a light sensitive resistor. Yeah, which the resistance of this night light sensor changes when daylight strikes it. A circuit detects this change and turns off the light during the day. And if it is dark, and then the circuit also detects the change and turn on the light during the night. Yeah, that makes sense to you? Okay. This is some applications for resistors. Yeah, let's talk about this conceptual example. The charging current in a toaster. Yeah, when you press the lever on a toaster, a switch connects the heating wire to 120 volt. The wires are initially cool, but the current in the wires raises the temperature until they are hot enough to glow. As the wire heats up, how does the current in the toaster change? Yeah, actually we can use the equations we talked before. Yeah, we know as the wire heats up, its resistivity increases as noted above. So the resistance of the wires increases. Yeah, we talk about in here. Uh, Let me find it to you. Yeah, here, yeah, like the resistivity of a metal increases with increase in temperature. Yeah, and let's continue to talk about the example. Yeah, as the wire heats up, its resistivity increases, and because the potential difference stays the same, an increase in resistance causes the current to decrease. Yeah, because we know from the Ohm's law, I equal delta V divided R. Yeah, this one keeps same, and this one, if it increase, and the current will decrease. The current through a toaster is largest when the toaster is first turned on. Yeah, does it make sense to you? Okay. The result, yeah, this is yeah. So let me see. Yeah, which means as a wire heats up, the current will become smaller. Yeah, and this result makes sense. As the wire's temperature increases, the current decreases. This makes the system stable. Yeah, if you can imagine, if instead the current increases as the temperature increased, higher temperature could lead to more current, leading to even higher temperature, and the toaster could overheat. Yeah, can you imagine that? Yeah, which means this result makes sense. Okay, let's continue to talk how to analyze a simple circuit. Yeah, you can see in a light bulb, connections to the filament in a bulb are made at the tip and alongside the metal cylinder. Yeah, yeah, it is useful to think of a light bulb as a resistor that happens to give up light when a current is present. Yeah, you can see here. This is a light bulb. This is a filament, and this is a connecting wire. Yeah, and this is which means this light bulb is just we can consider it as a resistor. Yeah, does it make sense to you? Okay. In a circuit using a battery, a light bulb, and a wires, yeah, a flashlight, the light bulb has a resistance of around 3 ohm. The wires typically have a much lower resistance. Yeah, so we can ignore the wire's resistance usually. We use an ideal wire where its resistance is zero. The potential difference in the wire is zero because the resistance is zero. That makes sense to you, even if there is current in it, because this is just like a no exist, because we just consider it as the resistance is zero. Okay, then for the ideal a wire model, two wires are connected to a resistor because we consider the bulb as a resistor. Yeah, and current flows through all three, but the current only requires a potential difference across the resistor. Yeah, you can see here the current is constant along the wire resistor wire combination. Yeah, from here to here, the current is the same. Yeah, in the ideal wire model, there is no voltage drop along the wire, which means here, the voltage here, the voltage here is the same thing. And the voltage here is the same thing. Only drop from here to here, the voltage drop. Yeah. All the voltage drop is across a resistor. Yeah, that makes sense to you? Okay. Yeah, current moves in the direction of the decreasing potential. So there is a voltage drop when the current passes through the resistor left to right. Yeah, there is a current drop here if the current direction is here, which means the voltage will drop. Compare with this point, in this point, the potential, the voltage will drop. Okay, and the electrical field in a resistor carrying a current in a circuit is uniform. Yeah, and the strength of the electrical field is this one. We can using this equation to represent the strength of electric field. Yeah, the electric field inside the resistor is uniform and point from high to low potential. The current is in the direction of the decreasing potential. Yeah, this is for the electric field in a resistor. And let's check one quick check question. In trial 1, a battery is connected to a single light bulb and the brightness noted. Now in trial 2, a second identical light bulb is added. How does the brightness of these two bulbs compare to the brightness of the single bulb in trial 1? We know the current larger and the bulb will brighter. Does it make sense to you? Okay, for this one, the I equal R divide sorry, no, R divide. Yeah, the V divide R. Am I right? So for the trial 1, the R is only one R because only one bulb. But for the trial 2, which means the current equal V divide 2R because there are two different resistors. Am I right? So which means this R2, this is R1. Yeah, the voltage is the same thing. Yeah, which means the R2 is smaller. Yeah, which means the brightness is greater. For in trial 1. Does it make sense to you? Yeah. Yeah. This question just ask how does the brightness of those two to compare with the brightness of a single? Yeah, the two will be the brightness is less. Yeah, that makes sense to you. So we need to choose C. Yeah, if this question asks you what the brightness of single bulb in trial 1, it will be greater. Okay, let's continue to talk about this example using a thermistor. Yeah, a thermistor is a device whose resistance varies with temperature in a well-defined way. A certain thermistor has a resistance of this 2.8 k ohm at 20 degree and this 0.39 k ohm at 70 degree. And this thermometer is used in a water bath in a lab to monitor the temperature. The thermometer is connected in a circle with a 1.5 volt battery, and the current measured. What is the change in current in the circuit as the temperature raises from 20 degree to 17 degree? Yeah, actually we can use the Ohm's law. Yeah, we can use I equal what? Equal R. Oh, sorry, I just write it. Equal V divide R, am right? And for the 20 degree, and it is one. This is the voltage, and this is the resistor. And for the 70 degree, and the voltage will be the same thing, but the resistor changed. It is just 0.39 k ohm. Yeah, you can calculate the current. Yeah, in different situation. Yeah, this is what we just write down. Yeah, and this is the current for the 20 degree. This is the current for the 70 degree. This change in current is 3.3. Yeah, because you can 3.8 m a minus 0.754, and then it will equal around 3.3. Yeah, a modest change in temperature leads to a large change in current, which is reasonable. This is a device intended to provide a sensitive indication of a temperature change. Yeah, Okay, let's continue talk about energy and power. Yeah, you can also review some videos for the current and resistance part 3, energy and power. Yeah, I will now talk about it. I will now play it here. Okay. Yeah, a battery not only supplies a potential difference, but also supplies energy. Yeah, we talk about that in last class, because there are the electric field inside it, and which means there will be some energy. Yeah, the charge escalator transfers the chemical energy. We call it E chemical to the electric potential energy U of the charges. Yeah, we talk about in last class for the battery, and there are some chemicals, and these chemicals can escalate the charge from the negative to the positive. Yeah, and which means the charge escalator transfers chemical energy to the electric potential energy. Yeah, that energy is then dissipated as the charges move through the light bulb, keeping the filament warm and glowing. Yeah, this energy, this like a potential energy, uh, like be dissipated as the charges move through the light bulb, keeping the filament warm and glowing. Yeah, yeah, like this is just the figure for this process. Yeah, the chemical energy in the battery is transferred to the potential energy of the charge in the current, and then the charge lose energy in the collision as they pass through the filament of the bulb, and this energy is transformed into the thermal energy of the glowing filament. Yeah, this is all the energy in the real world is just keep the is a constant, and if the chemical energy here the total energy actually is the same. And if the chemical energy decrease and the potential energy increase, and then the potential energy decrease, and then the thermal energy will decrease. Yeah, but the total is constant. Yeah, this is a conservation of energy. Okay, a charge Q gains potential energy. Yeah, we know this from the chapter 21 and 21, 22. Yeah, this is the equation for the potential energy change. Yeah, as it moves through a potential difference delta V. Yeah, the delta U equal Q delta V, and the potential difference of a battery is this one. Yeah, we talk about this in last class. So the battery supplies this potential energy, uh, like uh, to charge Q as it lifts the charge up the charge escalator from the negative to the positive terminal. Yeah, this is just the energy the charge use to lift the charge up, the charge escalator from the negative to the positive terminal, and then the rate at which energy is transferred from the battery to the moving charges is this one. This is rate of the energy transfer, which means the energy potential energy difference. Yeah, here. This is a potential difference of a battery, and this is the time, which means in this time and this a potential energy change. Yeah, which this is the rate of the energy transfer. Yeah, we use this symbol P bat to represent this, and this because delta U equal what? Equal delta Q. This ellipse. Yeah. So then we can get this equation. Yeah, does make sense to you? Okay, and here delta Q divided delta T, the rate at which charge moves through the battery is the current I. Yeah, we talk about this in last class. I equal delta Q divided delta at the beginning of the last class. This is if you know the charge change and in a unit time, you can get the current. So which means this rate of energy transfer can be read as this equation. I multiple like the multiple the this like the potential difference of a battery. Yeah, and this is power delivered by a source of EMF. I actually this is similar with V like that, IV like that. That makes sense to you? Okay. The power, this is we call it defined up is power. Actually, the power is the rate of the energy transfer. Yeah, and we can use this equation to calculate it. And the power has unit of joule per seconds or watt. Yeah. Okay. Let's talk about an example. Power delivered by a car battery. A car battery has like the potential difference like 12 volt. When the car's starter motor is running, the battery current is this one. What power does the battery supply? Yeah, we can use this equation. Yeah, the power equal I multiple uh, uh, like a potential difference of that battery. Yeah, we call it EMF. Yeah, and then the power is the product of the EMF battery and the current. Yeah, so the current we use this equation to calculate, and the current is 320 ampere, and the EMF is 12 volt. So this is the power supplied by the battery. Yeah, this is a lot of power actually. It is about 5 HP. Yeah, horsepower. Yeah, but this amount makes it sense because turning over a car's engine is hard work. Car batteries are designed to reliably provide such intense bursts of power for starting the engine. Yeah, actually, yeah, this power is big, but to start a car, you need a big power. Yeah, doesn't make sense to you. Okay, let's talk about this like those example problems in the okay, let's try to review this one. And an electric kettle has a coiled well inside that dissipates power when it carries a current, warming the water in the kettle. A kettle like designed for use in England carries 30 and when connected to a 330 volt outlet. What is the resistance of the wire? Yeah, actually, from the Ohm's law, yeah, we know the R equal V divided I, am right? So the V we know is 330 volt and current is 38. So which means it is around 80 ohms. Yeah, and what power is dispatched when the kettle is running? Yeah, we know that the P equal V I, am I right? So like we know the V and we know the I, yeah, and divide like 30. It's around 3 kV. Yeah, you can calculate by yourself. Yeah, let's check. The question C, the kettle can hold 1.7. This is L, like a liter L of water. Assume that all power goes into heating the power. How long will it take for the kettle to heat the water from 20 degree to 100 degree? Actually, the heat transfer, yeah, I think you have already learned in chapter 12 in college physics 1. If you forgot it, and you can review it. And actually, like the energy required uh, is Q equal mc delta T. This is the temperature difference, and this is the the specific heat capacity of water. This one is a constant value, and this is like a mass of water. Yeah, since here is 1.7 liter in water, which means the 1 liter is equal 1 kilogram. So here is 1.7 kilogram like water. So which means the energy required is 1.7 multiple. This is a constant. It is equal 4186 G per K, and this T, yeah, because the difference is 80 degree, so this one is 80 degree. Yeah, and you can calculate the like the energy required. It's around like five 568,000 and 16 G. Yeah, it's around this value. And then we know like the like power, yeah, equal Q divided T. This is time, so T equal Q divided power, and this is Q, and this is the power is here around 3 kV. So the T is Q divided P around like 119 seconds. Yeah, actually this equation you can find it in like chapter 12. Yeah, and yeah, this is the T. If the kettle to heat the water from 20 degree to 100 degree. Okay, let's check the next one. What is the yeah, and the kettle in the previous example is now redesigned to work at the lower voltage of outlets in the United States. Now the kettle carries 30 ampere, will connect to 120 volt. You can see here. This is like a 30, and this is the volt. For this question is 230 volt, but here it is 112 volt. Yeah, 20 volt. So what is the new resistance of the wire? So we just use the equation R equal V divided I. Yeah, 130. Yeah, so what's the answer? Yeah, you can quickly. Yeah, it should be around 9.2 ohms. Yeah. And how long will it take for the redesigned kettle to heat 1.7 liter water from 20 degree to the 100 degree? Actually, this one is a similar similar question with C question. Yeah. And we know like here we can calculate the new power, and then the Q, it's the same thing for this one. Yeah, because everything is now changed. The mass, the constant, and the like degree differences. So this Q is the same value, and only the P is changed because here it is 120 multiple 30, and then you can calculate the new new P, and then you can calculate the new T. Yeah, I will leave this question to you. Yeah, and this is around like is around like 6 minutes. Yeah, you can calculate by yourself. Okay, let's continue to talk about the energy and the power. In a circuit consisting of battery and a single resistor, the entire sequence of energy transformation is actually we talk about this a little bit. Yeah, firstly the charge gain potential energy U in the battery from the electric chemistry like chemical like energy. Yeah, and then this chemical energy, yeah, like I said, transferred to the energy, potential energy. Yeah, and then this potential energy, across this wire or well, 然后 as charges accelerate in the electric field in the resistor, the potential energy is transferred into the kinetic energy key. Yeah, it will, because it runs, it moves, so it will transfer to the kinetic energy. And finally, and when it goes through the resistor, and then it will transfer to the thermal energy, EH, yeah. And you can see collisions with the atoms in the resistor transform the kinetic energy of the charges into thermal energy, yeah, ETH of the resistor. Yeah, that's the reason why the bulb or some resistors after a time and you touch it, it is a little warm or hot. Yeah, does it make sense to you? Okay. Yeah, this is like energy transformations. Yeah, and the net result of a circuit consisting of a battery and a single resistor is that the battery's chemical energy is transferred to the thermal energy of the resistor. Yeah, reason is temperature. Yeah, like this is a process for the energy transformation. You can see at the beginning it is chemical like energy, and at the end it is thermal like energy. Yeah, so this is we know like the battery's chemical energy is transferred to the thermal energy of the resistor. Reason is temperature. The rate at which that the energy is transferred from the current to the resistor is, yeah, this is we talk about it. Yeah, this is the rate. Also we call it the power. Yeah, it is equal like the delta U divide delta T. Yeah, and the delta U equal delta Q multiple delta V. Yeah, and delta Q and delta T divide delta T, we talk about that it is I current. So which means the power equal I multiple the potential difference. Yeah, we talked about this equation just now. Yeah, and the power equal this one, also equal this one, also equal this one. Okay. Yeah, in a single resistor circuit, and the circuit is the same in the battery and the resistor. Yeah, like the single resistor circuit, like this one. Yeah, this is just a single resistor, and yeah, the current is the same in the battery and the resistor. Yeah, so we know like the P resistor equal like power resistor for the power equal the power battery. You can see here if the current is the same thing. Yeah, and then the like the potential difference, we know that it's also the same thing. Yeah, because the wire we consider it is the ideal wire. There is no resistor in the wire. Yeah, that makes sense to you. So these two value equal with each other. The power dissipates in the resistor is exactly equal to the power supplied by the battery. Yeah, the rate at which the battery supplies energy is exactly equal to the rate at which the resistor dissipates energy. Yeah, this is just those three is just for the single resistor circuit. Yeah, just remember that. Okay, let's talk about one example, finding the current in a light bulb. How much current is drawn by a 25 volt light bulb connected to a 120 volt outlet? Then we know P, we can got it from this equation. Yeah, we know P equal what? P equal R V IV. Now we know the P, we know the V, we can calculate the current. That makes sense to you. The actual equation 20.10, yeah, this one relates the current to a power dissipated in the bulb and the outlets EMF. This is yeah, we can model the light bulb as a resistor. And because the light bulb is operating as intended, it will dissipate 75 volt power. We can rearrange equation 20.11 to find yeah, we know the PR equal I VR, so which means I equal PR divided VR. Yeah, so we just use this equation to calculate the current. It's around like a 0.63. And yeah, we've said that we expect the current on the order of 1 and for light bulb and other household items. So our result seems reasonable. Yeah, we talked about this just in this class later, just earlier. Yeah. Okay, let's talk about continue to talk about energy and power. Yeah, a resistor obeys Ohm's law. Yeah, we know that. Yeah, this is Ohm's law. Yeah, thus P. Yeah, because P equal this one, and then you can. Mm, you can rearrange this equation. Delta VR equal IR. That makes sense to you. So which means this will equal I square R. And also you can see here, because I equal this one, so which means PR also equal, you just put this here. Yeah, and it is V R square divide R. That makes sense to you. Yes, we can also use this equation or this equation to calculate the power. Is the power dissipated by resistance R with current I and the potential difference delta VR. The power varies as the square of both the current and the potential differences. Yeah, you can see uh, if the like a square of the current changes and the power will change, and if the square of potential difference changes, and the power also different changes. Yeah. So you can also review this class video, like practical electric applications to view some applications for this energy for these power equations. Okay, let's review some like quick check questions. A resistor is connected to a 3-volt battery. The power dissipated in the resistor is 1 volt, and the battery is treated for 3-point volt battery. The power dissipated by the resistor is not. Yeah, which means here we can got the P. We know P equal I like I uh I delta V R. Am I right? Yeah, which means here uh we know the P and we know the voltage differences, and we can calculate the I equal V divided delta V R equal 1 divided 3. Yeah, and then the battery is treated for the 6-volt battery, and which means the uh, the power like uh, yeah, which means the resistor is now changed, so we can now use this equation. We need to use the this equation to calculate the resistor firstly. Yeah, which means we need to use P equal VR square VR square divided R, which means R equal delta VR square P. And here it is 3 square divided by 1. So which means the resistor is 9 ohm. And then for the like 6 voltage, the power, yeah, you just the resistor will now change. So the power will change to 6 squared 36 and divide 9. Yeah, that makes sense to you. Okay, so the final result will be around 4. Yeah, that makes sense to you. Yeah, this one. Okay, let's continue. Okay, let's continue. Yeah, to check this question. Several light bulbs, different related voltages, powers. Which one has the highest resistance? Yeah, we also can use this P equal delta VR square divided R. Yeah, so the resistor will equal delta VR square divided P. So which means the first one, the resistor is 100 divided 1, it is 100 ohm, and this one is 16, because the square 16 divided 1 equals 16 ohm, and this one is square is 144 divided 2, which means it is 72. And this one square is 18, and this one square, yeah, divided 3 is 3. So the highest should be this one, 100 ohm. So the answer should be A. That makes sense to you. Yeah, you just use this equation. Okay, let's talk about that. The other one, which has a higher resistance, like a 16 watt light bulb or 100 like a watt light bulb. Yeah, actually, I think this one we also can use yeah the equation for like E for delta VR squared divided R. Yeah, we can also use these equations. Yeah, we both use at delta uh, voltage. Yeah, I think this one missed some information. Yeah. Okay, sorry. I think this question is just miss some information, and this question need to tell us like the voltage different, the potential voltage, the potential energy or the voltage is 120 volt. Otherwise, we cannot get enough information to tell. Yeah, just notice this question. Yeah, you should give this information, or we cannot get the which one is greater. Yeah, if we know this one is with the voltage is 120, which means the R equal delta V squared divided P, which means if P is smaller, the resistor will be higher. Yeah, so this one will be right answer. But if the question didn't give us this, and the answer should be there is not enough information to tell. Yeah, okay. Let's talk about one example, like finding the power of a dim bulb. How much power is dissipated by a 16 volts, like a 120 volt light bulb when operated using a dimmer switch at 100 volt. Yeah, we will find the resistance bulb from the like 60 volt it dissipates at 120. That we use P equal delta V R square divided R to find the resistor. The resistor equal delta V R square divided P. Yeah, and this one is 120 square divided 16. Yeah, and then we can get this resistor, and then for like 100, we know the resistor, we can calculate the power. That makes sense to you. Yeah, the 16 volt rating is for operation at 120 volt. We will assume that the resistance doesn't change if the bulb is run at a lower power. Not quite right. Actually, yeah, in the real in the real world, the resistance will change if the bulb is run at different power. But yeah, ideally, yeah, we just consider it is the resistance will not change. But a reasonable approximation for this case in which the voltage is only slightly different from the rated value. Yeah. Okay. The bulb display, yeah, we talked about this just now, and then we can got the filament resistance. Yeah, using this equation, it is 240 ohm. The power resistor when operated, this one we just like this is 240 volt ohm, and this is 100, and then we can get the new power 42 volts. Yeah, that makes sense to you. Yeah, reducing the voltage by 17% leads to a 30% reduction of power. You can see here. Yeah, we just reduce the voltage from like 120 to 100, which means the voltage will reduce by 17, and there will be the power like a decrease from 16 volt to 42 volts. Yeah, so which means like a 30% reduction of power. This makes sense. The power is proportional to the square of volts. Yeah, so we expect a proportionally larger change in power. That doesn't make sense to you? Okay, let's talk about this example problem. Yeah, this example problem, let's read it firstly. Yeah, an electric blanket has a wire that runs through the interior. A current causes energy to be dissipated in the wire, warming the blanket. A new low voltage electric blanket is related to be used at 80 volt. Yeah, it dissipates a power of 82 watts. What is the resistance of the wire that runs through the blanket air? There are so many information, but what we just need to pay attention is this is the voltage and the energy potential difference, and this is the power. So we can use this equation P equal V squared divided R. So which means the R should equal V squared divided P. Yeah, this one should equal this one. Yeah, that makes sense to you. And the resistor will around 4 ohm. Yeah. Okay. And let's talk about this one. Many websites describe how to add wires to your clothing to keep you warm while riding your motorcycle. These wires are added to the clothing. A current from the 12-volt battery of the motorcycle passes through the wires, warming them. One receipt for a vessel calls from 10 meter of 1.25 millimeter diameter copper wire. How much power will this vessel provide to warm the wire? Yeah. Firstly, let's talk about the power. We know here we know the voltage, and then when we just need to know the resistor. Yeah, we can got V square divided R to get the power. Yeah, here we just need to calculate the resistor. We know the voltage here. The resistor equal what? Resistor equal this real multiple L divided A. Here it is copper, so we can so the value it's around 1.7 multiple. Yeah, this value is just for this copper wire, and the length we know it is 10 meter. Yeah, and then the area is because the diameter is 1.25, which means R equal 0.125 meter. Yeah, and then the area is pi R square, and you just pi this one square, and then you can calculate the resistance, and from this equation you can calculate the power. Yeah, I will leave this question to you, and the final result is around 41 volts. Yeah, you can use this equation to calculate it. Okay, this is what we talk about in this class. We talk about the relation connecting the how potential and current connecting, and we know the potential energy. The energy potential is just a voltage. So we use the Ohm's law to connect the potential and the current. And during this law, and in this law, we also talk about we need a resistor. So then we talk about the Ohm's law and the resistor circuits, and we know how to calculate the resistor, depend on the material features. Yeah, and also we learn the energy and the power, and we know like during the electric circuit, and there are some like energy transformations, and also we know like how to calculate the power during these transformations. Yeah, this is what we talk about in this class. Okay, let's do a summary. Yeah, there are also some like videos you can check for to summarize these things. Yeah, I will not play it here. And yeah, you can see here. Firstly we talk about the batteries, resistors, and current. And we know the current is defined to the motion of positive charges. Yeah, we can use this equation to represent the current. And you can see for this is a current at this is a circuit, and for this one there is a battery. Yeah, the battery is a source of potential difference. Yeah, chemical processes in the battery separate charges. We use a charge as escalator model to show the lifting. Yeah, here lifting of charges to higher potential, and the battery transforms its chemical energy into electrical potential energy of the charges passing through it, raising their like electric potential. The potential difference on the battery is its EMF. Yeah, using this symbol. Yeah, we calculate in last class. We talk about this in last class. Yeah, and then we talk about the conversation of current. Dictates that the current is the same at all points in the circuit. Yeah, the battery creates an electric field in the circuit that causes charge to move. Yeah, positive charges move in the direction of the electric field, which is the direction of the decreasing potential. Yeah, we talk about this in next class. Random collision of charges with the atoms impede the flow of the charges and are the source of resistance. Yeah, the collisions increase the thermal energy of the resistor. We use the ideal well model in which we assume that there is no resistance in the wire. Yeah, this is just a we talk about it in last class and this class, like here is a battery. The battery, firstly, there are some chemical energy. This chemical energy will be transferred to the electric potential energy, and then as the charge move and the electric potential energy will be transformed to kinetic energy, and then those charges go through this resistor, and the kinetic energy will be transferred to the thermal like energy because the conclusion. Yeah, this is what we talk about in this class. Okay, and then we talk about the resistivity and the Ohm's law. Yeah, the resistivity, this rule is a property of a particular material. Yeah, in for the specific material, this resistivity is a constant like that, but for different materials have different resistivity. Yeah, good conductors such as copper have low resistivity. Yeah, which means it has a low resistance. Yeah, poor conductors such as pure water have high resistivity. Yeah, the resistance is a property of a particular wire or conductor. The resistance of a wire depends on its resistivity and dimensions. Yeah, actually the resistance of a wire like is depends on the resistivity and the dimensions. Yeah, and this is the resistivity, and this is the length, and this is the cross section area. Yeah, these three things, like they said, the resistance for one material. Yeah, and then we talk about the Ohm's law. Yeah, Ohm's law describes the relationship between the potential difference across and the current in a resistor. Yeah, this is the Ohm's law. Like the current equal the voltage difference, like the potential electric potential difference divide R. Yeah, this is Ohm's law. And then we talk about the energy and the power. The energy used by the circuit is supplied by the EMF of battery through a series of energy transforms. Yeah, we just talked about just now, the chemical energy in the battery transformed to potential energy of separated charges, and then transform to kinetic energy of moving charges, and finally transform to thermal energy of atoms in the resistor. Yeah, this is what we talked just now. Yeah, the battery supplies power at the rate. Yeah, this one. This is the battery supplies the power, and this is the resistor displays power at rate. Yeah, using this equation. Actually, if there is only one resistor circuit, yeah, it's a one resistor circuit. These two should be equal. Yeah, because this one, like the EMF, should equal the electric potential difference for the resistor. Does it make sense to you? Yeah, this is what we talked about in this class. And also we talk about the conducting materials. When a potential difference is applied to wire, if the relationship between potential difference and current is linear, the material is, we call it like ohmic. Yeah, the resistance is equal this one. Yeah, because you can see we know like I equal delta V divide R. So which means uh, equal 1 over R multiple delta V. Yeah, which means this is a loop. 1 over R is this slope, which means R equal 1 over slope. That makes sense to you? Yeah, and resistors are made of ohmic materials and have a well-defined value of resistor using this equation. Only the ohmic material can use the Ohm's law. Otherwise, it cannot be used for the Ohm's law. Yeah, just a bit attention to that. Yeah, we also talk about the batteries in series. Yeah, batteries connect to one after the other are in series. The total potential difference is the sum of the potential difference of each battery. Yeah, for example, here is this is the EMF for the battery 1, for the battery 2, for the battery 3. The total is just those three plus together. Yeah, we talk about that in last class. Yeah, yeah, this is all we talk about in the chapter 22. Yeah, you can review all these things when you are available. Actually, this chapter, the content is not that much, and uh, it's quite it's quite it's not that much, but it's very important. Yeah, those things can help you to analyze all the circuits like later. Yeah, and you if you need to remember all those things we talk about. Yeah, okay. If you have any question, just let me know. Email me, text me, or find me in my office hour. Okay, thank you.